Let's take a look at deriving a formula for a banked curve. What we're going to say is a car is traveling with a speed v around a curve of radius r, but we don't want friction to matter. So what angle should we make it so that friction doesn't matter? Okay, as always, I'm going to start with the picture so I can keep track of all the forces. We'll label everything we know and solve for what we don't. Okay, so this is supposed to be my bank curve. Remember, that's actually curving around away from us, and this car is traveling along this curve, and it's not getting further up the incline or further down the incline. It's just hanging out right on the incline. Okay, and the radius of this curve, the center of this curve, is somewhere over here. And we're told that the distance from the car to the center is r meters, and we're told it's traveling at a speed v. So our speed equals v, our radius equals r, our angle is what we're trying to find. We don't know what it is. What angle should we be using so that this does not require friction, which tells us one more piece of information. It tells us friction is 0. We're not going to have to worry about it. So we want to establish our frame of reference and label all our forces. First thing to note is this is a constant radius r. It's not drifting up the incline and getting further away. It's not drifting down the incline and getting closer in, which means it's not accelerating along the incline. The only acceleration we have is the centripetal acceleration, which is acceleration towards the center, AC. Well, if that's the direction of my acceleration, that's the direction I want to choose for my frame of reference. So I'm going to call this the positive x direction, and of course y is 90 degrees to that, so there's the positive y direction. So when I come and I actually label my forces, I have the force due to gravity, which acts straight down. It's all in the y direction. And I also have the normal force, which acts perpendicular to the surface, up and right. It's not all in the y direction or all in the x direction. It's got components in both. So of course I want to go ahead and deal with both of those components and label them, put them in. So this is the normal force, this is the normal force in y, and this is the normal force in x. Alright, now we're supposed to find a formula for the angle theta so that we don't need friction. So let's see what we know. We know that the net force in the x direction is equal to the normal force in the x direction, because that's the only force that's in my picture that actually acts in the x direction. And since the only acceleration we have is AC, this is equal to mass times centripetal acceleration. That's Newton's second law. Net force equals mass times acceleration. Alright, we're supposed to derive a formula for theta, so let's see. From this I can say Fnx is really Fn, but it's opposite this angle. Now this angle and this angle are the same because they're similar triangles, so I have Fnx is really Fn times the sine of theta is equal to m times v squared over r, because v squared over r is centripetal acceleration. Well, now I'm stuck because I have an unknown in this equation, m, and another unknown in this equation, fn, two unknowns and the unknown theta. I need more information. So I'm going to go ahead and I'm going to move into the y direction. The y direction is a little bit simpler. The net force in y, there's two of them, fny minus fg, but it's 0 because remember this thing is not drifting up or down the incline, it's not accelerating in y at all. So that tells me the normal force in the y direction is equal to the opposite of the force due to gravity. Now this is a little bit interesting because normally the normal force in y is exactly, or the normal force and the y component of gravity are the same, but this time it's the y component normally of the normal force in gravity. So the normal force is actually bigger than the force due to gravity because the car is pushed into the ramp as it turns the corner, so the ramp pushes back. That is a little bit of extra force. Alright, so now I have this formula involving Fny and Fg, but remember Fg is really just mg. So now I have Fny equals mg. However, Fny is the adjacent side of this triangle, so that tells me Fn cosine theta. So Fn cosine theta equals mg. And I can actually go ahead and then say, alright, that means the normal force equals mg divided by the cosine of theta. And now I can put this in to this equation, and we're going to see some of our unknowns drop out. So instead of Fn, I have mg divided by the cosine of theta, and then I'm going to go ahead and have the rest of my formula times the sine of theta equals mv squared over r. Well, mass is on both sides now, so it's gone. The sine of theta divided by the cosine of theta is the tangent of theta. Still have that g to deal with, and it's equal to v squared over r. All of a sudden, this problem just got a whole lot simpler. I can divide both sides by g, so the tangent of theta is equal to v squared over g times r, and then I can take the arctangent, or on your calculator, that's the tangent to the -1 power of both sides, so tangent or arctangent of v squared over g times r is equal to the angle we want to bank this road at so that friction is not required to turn the corner. We're going to take what we just did and extend that. Now we're going to say, okay, what if there is friction? How fast or how much friction is required to actually turn this corner? So now I'm giving you a little bit more information. I'm telling you that we have a bank angle of 20 degrees. So this angle is 20. I'm telling you that the radius is 60 meters and the car is traveling at 18 meters per second. Now our last formula said that the bank angle should be the arctangent of v squared over r times g. If I do that real quick, if I take 18 and square it, and I divide that by the radius, 60, times the acceleration of gravity, 9.8, and I take the tangent of that, making sure my calculator is in degrees, then I see 28.85. That tells me we should have a bank angle of 28.85 degrees so that friction is not required. But I only have a 20-degree angle, which means we're going to need some friction, and friction is going to have to help us turn the corner. So again, acceleration is towards the center, so I'm going to have my x and y parallel and perpendicular to the world instead of the bank angle. So we're parallel and perpendicular with gravity. My car is up here, and we've got the force due to gravity acting on it, Fg, pulling straight down, and then of course the normal force is acting perpendicular to the road, Fn, and it's got its components, Fny and Fnx, and we have one more force. We have friction. This thing is going too fast. It needs a steeper angle, which means friction is actually going to be providing some force to help it turn the corner to prevent it from drifting up and out. So friction is actually acting along the incline this way. So this is Fs, static, because we're not sliding. It also has components because this is along the incline, not in x or y. So I have Fn, x, and I have Fn, y. It is worth noting on both of these that this angle down here is the central angles here and here. Okay, so those two angles in the middle are the same angle, the 20 degrees. So now when I use my formulas, I'm going to have more forces to keep track of because I have more things going on. However, we're still saying this car is turning the corner, so that this means there is no acceleration in y. So the net force in the y direction, which is equal to Fny, because it's pushing up, it's positive, minus Fsy, that's, okay, this is friction, so Fsy, it's going down, minus Fsy, minus Fg is equal to 0. So I have lots of forces in the y direction, but I'm still going to have a net force of 0. And in the x direction, I have similar thing going on, except that I'm going to use the x direction. So Fnx is going in the same direction as the static friction in x. They're both towards the center, and this is mass times acceleration, and because the only acceleration is towards the center, that's mass times centripetal acceleration, AC. So these are things I have, and remember, I'm supposed to be finding the coefficient of friction required so that this can happen. So if we take a look, I'm going to try to start simplifying this and eliminating things I don't know. So I'm going to go back to the y direction. Fny is the side adjacent to my angle, so this is Fn times the cosine of theta minus Fsy. Well, this is the side opposite the angle in the friction curve, so minus Fs sine theta minus Fg equals 0. And I'm looking at a static friction and a normal force, and that reminds me, oh, I know a little bit about static friction and the normal force. Those are related. So I'm going to go ahead and simplify this one more time. Fn cosine theta minus, remember static friction is the normal force times the coefficient of static friction. Of course, I can't forget my sine, minus the sine of theta, equals, or nope, minus Fg equals 0. And then, of course, I could take this one step further because I know a little bit about Fg. Fg is actually equal to mg. So I have Fn cosine theta minus Fn mu s sine theta minus mg equals 0. So in the y direction I have the normal force and the coefficient of friction and mg, and those add up to 0. And what I'm trying to find is what this coefficient of friction is. So if I can solve for that, I'll be good to go. The problem is I don't know m, and I don't know the normal force, and I don't know mu s. So I have lots of unknowns going on here. So I'm going to go to the x direction, and we're going to be able to make some substitutions. Alright, so in the x direction I have fnx, but remember fnx, that's the side opposite this angle, so that's really fn sine theta plus fsx, that's the static friction in the x direction. This is the one adjacent to my angle, so plus fs cosine theta equals m, but this is v squared over r. And again, I have this relationship with Fs and the normal force, so I can simplify this again. Fn sine theta plus Fn mu s cosine theta equals mv squared over r. So now I have two equations dealing with the normal force, the coefficient of friction, and mass. So if we can get stuff with mass in it to go away, our life will be easier. So what I'm going to do is I'm going to go ahead and I'm either going to solve one of these for the coefficient of friction or the normal force. I think I'm going to go for the normal force for now, and I'm going to go in the y direction because it's equal to 0. So what I have is I'm going to go ahead and pull out the normal force. So I have, oh, well, okay, yeah, Fn times cosine theta minus mu s sine theta equals, I'm going to add that mg over, mg. Now I can actually divide both sides by cosine theta mu s sine theta, and I have the normal force. So the normal force is really just mg divided by the cosine of theta minus mu s times the sine of theta. So that gets me a substitution I can use to try to find the coefficient of friction. So I'm going to go ahead over to this side and I'm going to start putting all that stuff in. Everywhere I see Fn, I have to replace it with this whole thing. So Fn becomes mg over cosine theta minus mu s sine theta times, don't forget that sine theta, that's actually from our original equation, plus, here's Fn again, so mg cosine theta minus mu s sine theta, and then we've got to remember our mu s cosine theta equals mv squared over r. Happily, a couple things do happen right now, so we can get our math simpler. Namely, I've got mass here, and mass here, so those go away. And the other thing to remember is I know a whole bunch of these things. They're just numbers, so I can actually start to get rid of some stuff and simplify a little bit. So I'm going to rewrite my equation down here without the masses, and we're going to see what I have. I have g times the sine of theta over cosine theta minus mu s sine theta plus g times mu s times the cosine of theta over cosine theta minus mu s sine theta equals v squared over r. I actually know the numbers for V and for R. I know the numbers for theta. I know G. The only thing I don't know in this whole equation is mu S. Now, it might be worth it to start putting like terms together and doing some division and some simplification, or you can actually just start plugging in numbers. It's completely up to you. I'm going to do a little simplification first. So I see that these are a common denominator. So I have G sine theta plus G mu S cosine theta over cosine theta minus mu S sine theta equals V squared over R. Now I'm going to actually multiply both sides by this denominator because it's got that silly mu S in it and I don't know it. So now I have G sine theta plus G mu S cosine theta equals V squared over R, and this whole thing is multiplied by the cosine of theta minus the coefficient of friction times the sine of theta, and so now I've got this R that's divided on this side. I don't like that, so I'm going to go ahead and, well, actually that's just a number, so I can deal with that if I want, but I could distribute it through either way. Okay, so G sine theta, this is 9.8 times the sine of 20, so this is a number, plus 9.8 mu S times the cosine of 20 equals V squared, which is 18 meters per second squared, over R, which is 60, times the cosine of theta, which is the cosine of 20, minus mu S times the sine of 20. Now, if we take all this into account, we can do some algebra and we can simplify some things. So 9.8 times the sine of 20 is really just 3.35. 9.8 times the cosine of 20 is 9.21, so plus 9.21 times the coefficient of static friction equals 18 squared divided by 60 is 5.4. So this 5.4 has to be distributed to this whole parenthesis. So cosine 20 is 0.94 minus mu S, which I don't know, times the sine of 20. The sine of 20 is 0.342. And then I'm going to distribute that 5.4, so I have 3.35 plus 9.21 times the coefficient of static friction equals 5.4 times 0.94 is 5.076, 5.076 minus 0.342 times 5.4, 46 minus 1.846 times the coefficient of static friction. Now it's just a matter of combining like terms, so I'm going to go ahead and subtract over this 3.35 and add over that 1.846 mu S. So 5.076 minus 3.35 is 1.762, 1.726 I guess, and then 9.21 plus 1.846 is 11.056. So 11.056 times the coefficient of static friction equals 1.726, and now I can divide both sides by this 11.056, 11.056, and I see my static friction 1.726 divided by 11.056 is 0.156. It has to be at least 0.156 in order to turn this corner at that speed. It's a long, arduous process, but just remember, draw your pictures well, make all your substitutions, and do not forget to use components on your forces.